Hello and welcome to our Activity 2 simulated facilitated diffusion experiment on PhysioEx. So this is part of exercise 1, the cell transport mechanisms and permeability. We are already through with activity 1, simulating dialysis, simple diffusion. So now we will move on from simple diffusion into facilitated diffusion. We're also going to look at the similarities between simple diffusion and facilitated diffusion. And also, obviously, we're going to go into the details of the differences between simple diffusion and facilitated diffusion, because they are not the same. However, there are similarities and there are differences. So let's get into that. So it's very important to review the objectives because that helps us keep in mind what to look for in the experiment. So our objectives are to understand that some solutes require a transporter, a carrier protein to pass in order for them to pass through the membrane because of the size or the solubility limitations or the charge. So some ions, they need a carrier because we understand that the bilayer leaflet, the plasma membrane, it has a hydrophobic core. So only hormones that are lipophilic are able to dive through this bilayer leaflet, or any substance that is lipophilic can easily diffuse, but lipophobic or hydrophilic substance, they cannot participate, they cannot penetrate this hydrophobic core of the bilayer leaflet. So they need a transporter. So just because there is a concentration gradient from one side to the other, and there is more of a solute that happens to be a polar solute, that it should move from outside to the inside. It doesn't mean it can pass through. It needs a transporter. And these transporters, these are proteins, these are carrier proteins that mediate the passage of amino acids that are charged or that they are big in size, glucose that is huge in size, glucose or galactose or fructose, or any substance that cannot, except lipids, because lipids, they can easily, because lipids dissolve lipids, they can easily go through the bilayer leaflet of the membrane. We are going to observe how concentration of the solutes, how the concentration of the solutes affects the rate of the facilitated diffusion. And we're going to observe how the number of the transport proteins affects the rate of the facilitated diffusion. So obviously, the more substance that's it, the higher the concentration, the more quantity of solutes obviously increases the rate of the facilitated diffusion. But obviously, there is a ceiling effect, because if you keep increasing to a level where these carrier proteins are fully saturated, so they cannot be shuttled anymore. And that's the problem with diabetes. So patients who are diabetic, when we do the urinalysis and we examine their urine, obviously there is a lot of sugar in the urine. And the problem is because there is so much sugar in the blood, the transport maximum has been reached by these glucose transporters that are found in the kidney and are responsible for reabsorbing glucose. So all of them are saturated, and yet there is still more glucose to be reabsorbed, and that's why glucose escapes into the urine. So obviously the relationship is that the more you increase the solute, the faster or the higher the rate of facilitated diffusion, except when you overwhelm this carrier protein with excessive amounts of solutes to be transported, and the transport maximum has been reached, and there is a saturation. then there will be failure to reabsorb or to transport that substrate. So we're also going to observe how the number of the transport proteins is going to affect the facilitated diffusion. So we're not only going to look at the solutes, we're also going to look at what if we increase the number of these transport proteins. If we increase the number of the transport proteins, obviously we're going to increase the amount of substrate that will be transported. So the more seats we have, the more rides, the more shuttle that we have, the more we are able to pass extra and more quantity of solutes. We're also going to be understanding how transport proteins can be saturated, and I alluded to that when it came to diabetes, but we're going to talk more about that. So some molecules are lipid insoluble, meaning that they are polar and they may be too large and charged to pass through the pores in the cell membrane. Instead, they pass through the membrane by a passive process known as facilitated diffusion. So it's also a passive diffusion, just like passive diffusion. The only difference is we're not naturally flowing down a permeable membrane. What's happening here is we have an actual carrier. We have an actual protein that is mediating this passage. So for example, sugars, amino acids, and ions are transported by facilitated diffusion. And the carrier protein molecules in the membrane, they might have to change their shape slightly to accommodate the solute, but the cell does not have to expend energy. That's a very important distinction. So facilitated diffusion is very simple to simple diffusion in all aspects. The only difference is that in simple diffusion, we do not use a carrier. We do not use a facilitator, but we use the facilitator. We use this carrier protein when it comes to facilitated diffusion. So you can read this on own. We're going to be using left and right beakers and dialysis membranes. And we're going to use a membrane builder where we're going to be plucking in a number of glucose protein carriers. Okay, so let's begin with the pre-lab. So molecules need a carrier protein to help them move across a membrane because they are not lipid soluble. That is true. And because they are too large, both they are lipid insoluble and because they are too large. That's excellent. Okay, which of the following is true of the facilitated diffusion? The movement is passive and down concentration gradient. Yes. So that definition is also true for simple diffusion. The only difference is when it comes to facilitated diffusion, we have movement that is passive and down concentration gradient, but with a facilitator, with a protein carrier. Okay, examples of solutes that might require facilitated diffusion. Glucose, amino acids, sodium, that is that's a cation, positively charged, and so is potassium. Which of the following would not affect the rate of the facilitated diffusion? The amount of intracellular ATP. It does not use ATP. It does not use ATP. It is a natural process that is reliant on kinetic energy. Kinetic energy equals half mv squared. So we have a mass, and the mass of the solutes that are bumping to each other, they have energy that propels them to move down concentration gradient away from the stress of this kinetic energy and bumping into each other. Okay, so now this is the membrane builder. So here we can modulate and choose the number of the glucose carriers. When we click build membrane, this membrane here is going to have the number that we choose it to be. So now this is 450, that's 500. When we click build membrane, there's going to be 500 glucose carriers here. So now they want us to note that the glucose carrier display in the builder is 500. So click on build the membrane. So now that is 500 glucose carrier proteins. Then we got to put that right here. And then the next step, drag the membrane to the membrane holder between the beakers. We did that. And then we're going to increase the glucose concentration to 2 millimolars. And we have nothing to do with sodium chloride. And let's dispense that. So this solution that we dispensed on the left beaker contains what's on this board, which is 2 millimolars of glucose and 0 sodium chloride. Then we're going to add deionized water on the right beaker, and they are separated by this membrane containing 500 glucose transporters, glucose carriers that we have built here in this membrane builder. Then we're going to click on start, and this experiment is going to run for 60 minutes. And then we're going to look forward to equilibrium. We began with 2 millimolars, and equilibrium, we're going to have equal on both sides. So there was 2 here and 0 here. They will become equal when we have 1 and 1 on both sides. And equilibrium was reached at 43 minutes. So obviously this timer simulates 60 seconds, but it was compressed to less than that. But it took about 43 minutes. So this shows us that in our first run, we had 0 sodium chloride, and we had 2 millimolars of glucose, and we had 500 carriers, and the rate of the facilitated diffusion, the rate of carrying glucose from the left side to the right side was 0.0008 millimoles per second. So now let's move on to the next step. We have recorded the data. Now let's flush everything and let's move on. So now we're going to increase from 2 millimoles of glucose to 8. So now we're going to be testing increasing the quantity, the number of glucose solute particles. How will that affect our results? Everything is going to be kept the same. So we're going to, this is going to still remain at 500. So everything is going to be the same, except that we have increased glucose concentration from 2 to 8. We began with 2, but now we're going to run it with 8 to look at the rate. So that is our independent variable. Our independent variable is what we are not measuring, which is the glucose concentration. What we're measuring is the rate. How will that be affected? How will that change? Okay, and then we're gonna put deionized water on the other side, and then we're gonna run the experiment, and then we're gonna look at how long will it take for them to equilibrate. So we began with 8, so we're looking forward to 4 on both sides. Equilibrium was reached at 58 minutes. So let's record the data. So that shows you it was faster. So now we increase the number of glucose particles that led to an increase in the rate of the transport of glucose. Next step, let's flush everything. Now, what happened to the glucose transport rate when the glucose concentration was increased from 2 to 8? The glucose transport rate increased. Then drag the membrane to the membrane holder. Then we're going to then press flush. What effect do you think increasing the number of protein carriers will have on glucose transport? So if I increase the number of protein carriers, so I have 500. So if I go up to 600, 700, 800, I expect that there will be that the glucose transport rate will increase. So now we're going to go up to 700. So now this membrane is no longer going to have 500 glucose carriers plucked. It's going to have 700. So that's even more. That's 200 more glucose carriers. So let's build the membrane. So now it's being built. Okay. Yes, we did that at 700. Now let's see how much glucose. We're gonna begin with 2. So we're gonna repeat the experiment again. We're gonna dispense 2. We're gonna put deionized water. So now the only thing that's different is we increase the number of the transporters. Press start. Begin with 2, so they're gonna equilibrate at 1 on each side. Record the data. Okay. Now increase the glucose concentration to 8 now. And now we're gonna go up from 2 to 8. Then we're gonna dispense. Then dispense water. And we have 700 here. So now let's see, we're gonna look forward to being from 80 to 44 equilibrium at, and then we're gonna record the data. Reach at 43 minutes. So let's record the data. So when glucose was 2 millimoles compared to 8 millimoles, and we have the same 700 carriers, when we added more glucose, the rate was faster. So this reminds us of enzyme kinetics. In enzyme kinetics, the more substrate you add, the faster the reaction will be until all of the active sites of the enzyme have been, all the active sites have been saturated and we have reached Tmax, transport maximum. So the more you add substrate, the faster the reaction, except that you reach that point where there is no return, and then you have reached a point of saturation. So that's a very important home point, and that is if you increase the concentration, the reaction rate will increase. But you don't want to increase it too much. So if we go glucose from 2 to 8 to 800, then that's gonna destroy the reaction rate. Is not going to progress faster than its maximum. No, describe the conditions that resulted in the fastest rate. So obviously, the carriers, the more you increase the carriers, the faster the reaction rate. So one of these two, and the more you increase the substrate, the glucose. So it's definitely this one. So the more glucose carriers and the more glucose concentration will lead to the most optimal condition leading to the fastest reaction rate. Okay, now this is interesting. Decrease the number of glucose carriers to 100. So now we're going to move down, excuse me, from 700 into 100. So now we have dropped these carriers. So there are less boats to help us cross the river. So now we have built the membrane to go down from 700 to 100. So obviously that's going to drop the rate of glucose transfer. And now we're going to increase glucose concentration to be displaced in the beaker to a 10. We see to a 10. Then we're going to dispense that. Then we're going to dispense water. Then we're going to start a run. So we're going to equilibrate. We began with 10, so we should have 5 on both sides. So you see it's very slow because we have dropped the carrier. So now it shows you that equilibrium wasn't even reached. So that shows you that transport maximum has been reached, that these 100 protein carriers, glucose carriers, they are full and there is so much glucose waiting in line to be transported, and the time was just not, so the experiment ended too soon, these 60 minutes, and equilibrium wasn't even reached. Let's record that data. You see glucose, and it shows you that the rate was so slow, but the reaction did not go to completion. Why do you think equilibrium wasn't reached? Because the membrane proteins were saturated. Transport maximum, Tmax, has been reached. Okay, what effect do you think adding sodium chloride will have on the glucose transport rate? Sodium chloride has nothing to do with the transport of glucose. We know that, for example, if this was a sodium potassium ATPase, the more ATP you're going to add, the faster the reaction rate will be. The more you deplete ATP, the slower the reaction rate. So what effect do you think adding sodium? Sodium has nothing to do with the transport of glucose. Sodium chloride does not influence glucose transport. Sodium is being transported by its own sodium channels and chlorides by its own chloride channels. And both are dependent on the process of diffusion. So there will be no change in glucose transport rate, definitely. So now let's experiment with that. Let's flush everything. Let's clean everything up and drag the membrane to the membrane holder between the beaker. Increase the glucose. Two. So glucose is going to be 2. Did they want us to select build the membrane to insert 700 glucose? So now they want us to do 700. Okay, so let's do 700. Yeah, build 700, and they want us to make our glucose 2. We said there will be no change, and we put the 700 back. This is a 2. Then we're gonna dispense, and we're gonna dispense deionized water on this side. So this side has only deionized water, 0 sodium chloride, 0 glucose, while the left side has 2 millimoles of glucose. Now, let us start. Okay, so that was a mistake because we ran the experiment only on glucose. We needed to add 2. We needed to add. So let's start over. We still have our 700 carrier proteins. We needed 2 glucose, 2 millimoles of glucose, and 2 millimoles of sodium chloride, and then we're gonna dispense. So now this solution here that has been dispensed to the left beaker has 2 millimoles of glucose, 2 millimoles of sodium chloride, while on the right, we have deionized water. And let's run the experiment now. Let's see how will that affect the rate of glucose. So glucose equilibrium was reached at 33 minutes. So that is the typical, um, time it takes for equilibrium of glucose. That is 2 millimoles. So, and for sodium chloride, it was 8. But so that shows you that this still is the same. So when we started with glucose that is 2, with 700 mill glucose that is 2 with 700 millimoles, this was the reaction rate, 0.001. And now glucose is 0.001 also. So this is just a little inherent variability. That is a type error in the experiment. So that doesn't mean, you see 0.1 right here. So glucose, that was a 2, when put in the same container with sodium chloride, still the same as when glucose, you see here, 700 carriers, 2 millimoles of glucose, 0.001. Here, 2 millimoles of glucose, 700 carriers, still 0.001, even though we had sodium chloride at the same solution. So that explains to you that sodium chloride has nothing to do with the concentration, the rate of the transfer, the rate of carrying or transport, or the reaction rate of that facilitating protein. Congratulations, we are done. Let's submit. Let's go now to the post lab. What variables increase the rate of facilitated diffusion of glucose? So increasing the concentration of glucose, definitely. Increasing the number of membrane carriers, definitely. Increasing the concentration of glucose and increasing the number of membrane carriers, both. S. For facilitated diffusion, increasing the concentration of glucose on one side of the membrane is the same as making a really big concentration gradient. Yeah, making like a very big gradient. Like imagine you have a big buffet on one side, and then there's like a door, and then people who haven't eaten for like 3 days, and then you had another medium where people who haven't eaten for 2 days, and then people who haven't eaten for 1 day. So the people who are there for 3 days without food, they have a higher gradient. So the more you add on one, so the more increasing the concentration of glucose on one side of the membrane, you're gonna make the gradient really steep. So the more concentration of glucose you add, the more kinetic energy. So on one side, the more solute you add, the more, definitely more kinetic energy driving and powering the movement of that solute to diffuse from an area of a higher concentration gradient to an area of a lower concentration gradient through facilitated diffusion by a facilitator carrier protein. When all the membrane carriers are engaged or busy, we say saturated, transport maximum has been reached. Sodium chloride had no effect on glucose transport because sodium is not required for glucose transport in the simulation. That sounds like a good answer. Okay, explain one way in which facilitated diffusion is the same as simple diffusion, and one way in which it is different from simple diffusion. Obviously, both of them share one thing, and that is they move down concentration gradient. So both of them, they move down concentration gradient, and both of them, they do not require ATP. So they just are reliant on the kinetic energy of these molecules bumping into each other, and that movement powers their movement from an area of a higher concentration gradient to an area of a lower concentration gradient. You will never see facilitated diffusion or simple diffusion helping the diffusion of substance from an area of a lower concentration gradient uphill to an area of a higher concentration gradient. No, that's active transport. Facilitated diffusion and simple diffusion both happen downhill. They just help the movement of substance from these solids from an area of higher concentration to an area of a lower concentration. That's the similarity. And that they don't require ATP, they don't require energy. The difference is that simple diffusion is just going through a membrane, while facilitated diffusion, we need a protein carrier, facilitator. That's why they call it facilitated diffusion, because there is a protein carrier plugged in the membrane that facilitates the passage of this hydrophilic substance that cannot dissolve into the lipid bilayer and then facilitating its movement downhill. The larger value obtained when more glucose carriers were present corresponds to an increase in the rate of the glucose transport. Explain why the rate increased. How well did the results compare with your prediction? So what effect do you think increasing the number of proteins? Yes, so the more protein carriers that are available, the more chance that these solutes can have a seat in the carriers to help them and expedite their transport from an area of a higher concentration gradient to an area of a lower concentration gradient. Explain your prediction for the effect of sodium chloride. We said that sodium chloride is not involved in this reaction of facilitating the movement of potassium, of glucose or amino acids from an area of a higher concentration gradient to an area of a lower concentration gradient. So, but if we were dealing with secondary active transport, which is reliant on sodium movement. So we couple the movement of sodium from an area of a higher concentration gradient to an area of a lower concentration gradient to the movement of some other molecule. Then that will be adding more salt, more sodium chloride is going to affect that. It's going to increase the rate because there's more sodium on the outside trying to make it in. So we shuttle the movement. But here we do not use sodium. So this is just a simultaneous diffusion process that is reliant only on the kinetic energy. Let's submit. Did we get everything correct? Yes, we did. Okay. Thank you very much. That's the end. And